Welcome to another lecture in digital communication. In this lecture, we will discuss about the design of optimum detectors and what is maximum a posteriori probability criteria for the detection and what is the maximum likelihood criterion for the detection. Okay, and what are the likelihood function, how to define, and then we'll discuss what is the minimum distance detection. And then I will summarize in all these points related to optimum detectors. And then we'll do a numerical problem on this optimum detection. So this is receiver configuration where R of t is a received signal. This bold face R is denoting the received vector at the output of signal demodulator. The function of signal demodulator convert this received signal into the received vector. And this will be the input to detector, and detector will give the S hat. It is S hat denoted detected constellation point up. Okay. So in the previous discussion, we know that this received vector contain all the relevant information in the received waveform. Okay. So here our aim is to develop optimum decision rule based on observation vector R. So detector will use this optimum decision rule to determine what is the S hat. Okay. So in this we'll know how to decide optimum decision rule. We will discuss in these lectures. Assumption is there is no memory in a signal transmitted in the successive intervals. Okay, that is the assumption for this designing optimum decision rule. So in the vector form represent a received vector at the output signal demodulator can be written R equal to Sm plus n, where R is this n-dimensional vector. This is also n-dimensional vector, and this is also n-dimensional vectors. As you know that Rk is the projection of this received signal R of t on the basis kth basis function fk of t. Similarly, smk is the projection of sm of t signal on the kth basis function fk of t. Also, nk is the projection of noise signal n of t on the basis function kth basis function fk of t. Okay. So the transmitted signal vector, this is also known as SM, also known as transmitted signal vector. It is a point in constellation diagram. The noise vector at the output of signal demodulator is n dimension. Okay. In noise, it is a n dimensional random vector with independent identically distributed components, each R1, N1, N2, and so on. Each being a Gaussian random variable with zero mean and variance and not by 2. So PDF of, because random variable is characterized by its PDF, fully characterized by its PDF, so we can write the PDF of nk random variable of this n dimension noise vector. Okay. So distribution of noise vector in n dimensional signal space has a spherically symmetric because component of noise are independent and having same mean and variance. Okay. So what is the effect of this spherical symmetric noise in signal space? When your transmitted constellation SM the received vector in the signal space represent the transmitted signal Sm plus spherically symmetric noise. So suppose this is signal space, three-dimensional signal space for illustration. So this was constellation point. This is Sm. So received vector, due to received vector in presence of noise, will be a spherical cloud at this center will be this constellation point, like this. Okay, so this is received vector. Okay, the density of this cloud is higher at the center because we depart from S1 means less point, these points are less likely to received, can be centered at the this density of this cloud is higher at the center and become less as we depart from this, because likelihood of this occurrence of the point far away from the this center point center of this cloud is less. Okay, this is a geometrical interpretation of this received vector, that is a sum of transmitted signal vector plus n-dimensional noise. Okay, so now I will discuss MAP criterion. Okay, so what was our objective behind the optimum detector is to design a signal detector that make a decision on the transmitted signal in each signal interval based on observation of the received vector or in each interval, such that optimum in sense means probability of correct decision is maximized. Yeah, probability of wrong decision is minimized. Okay, so decision rule based on computation of posteriori probability defined like this. This is a probability. This PSM given R is the probability of the signal SM was transmitted given that received signal R is received. Yeah, no, because detector only know this received vector R. So detector will decide which was the transmitted message, a constellation points. So he will calculate this posteriori probability for each M. And decision criteria is based on selecting the signal corresponding to the maximum of the set of posteriori probability. So this is in this set there are capital M, this posteriori probability, and decision criterion is called maximum a posteriori probability, because this decision rule based upon this posteriori probability. So we'll call this max maximum a posteriori probability. Okay, so as cap will be equal to the max of this. This is decision rule. So using Bayes rule, a Bayes theorem, posteriori probability can be expressed as like this. Okay, so this probability, a posteriori probability Sm can be written as a probability of R given Sm into probability of Sm divided by sum of all this. This is conditional probabilities. Conditional probability R given Sm into probability of Sm, where okay, this is conditional probability of observed vector R given Sm, and this P of Sm is the prior probability of MS signal being transmitted. Okay, P, this is this quantity, this this is a observed vector. PDF observed vector can be written as like this. Conditional probability multiply with prior probability of the transmitted message in sum. From equation 4 and 5, yeah, you say this equation, we can notice that computation of posteriori probability require knowledge of prior probabilities P of Sm and conditional PD of F of R given Sm. Okay, so computational requirement for the posteriori probability is knowledge of prior probability and knowledge of conditional probabilities. Both are capital M probabilities. This is a computational requirement of MAP based detectors. Now we'll discuss ML criterion for the detection. The decision criteria in ML based detector is based on selecting the signal corresponding to the maximum of the set of likelihood function. This conditional probability R given Sm is also known as a likelihood function. So decision criteria is called the maximum likelihood criterion, and S cap will be determined based upon this max of this likelihood function. Okay, so computational requirement for ML is only knowledge of conditional PDF, that is known as a likelihood PDFs. Okay, and in this case, when M signal are equiparable, this prior probability will be 1 by capital M. Is signal are equiparable. Okay, so this is prior probability of a signal being transmitted. Substitute this in the posteriori probability. Okay, we can expand this. Now I will replace this 1 by M, here also 1 by M, so it is constant, so to cancel out, so now we will have this one, this expression. So we, when equiparable case, so this is a posteriori probability of Sm given R. So from this, if we want to maximize the, we can observe, if you want to maximize this a posteriori probability, that is equivalent to the maximize this likelihood function a conditional PDF. Okay, that's why when this prior probability is 1 by M for all M, that is equiprobable symbols, MAP rule is equivalent to the ML rule, because ML rule is this, but when M signal are equiparable, we'll find that these both rule are the same. Okay, now we'll discuss likelihood function. As we know that RK is a sum equal to the sum of SMK plus NK. So this conditional, this R given SMK is a conditional random variable, and that is a Gaussian nature. That mean is SMK and variance is n naught by 2. Okay, so we can write PDF like this. In case of AWGN, in the case of a AWGN channel, likelihood function of this received vector, conditional received vector R given Sm will be, because each RK are independent, uncorrelated, and Gaussian nature, so joint PDF can be product of individual PDF. This is k equal to 1 to capital N. Substitute this expression and simplify. I can write this. I can write this in vector form also. So now we have this likelihood function. Sometimes we can write log likelihood function. So I will take natural log of both side in equation 13. So I can write like this, because natural log of exponential of minus a is a minus a. Okay, so this term will be this, and 1 by this term will be this, because natural log of 1 by pi n naught power n by 2, that is minus n pi n naught power n by 2, that can be n by 2 and n pi n naughts. Okay, so this is equation log likelihood functions. So with the help of this 13 and 14, for ML detection, we have to maximize this likelihood function, because this likelihood function is a function of decaying exponential, like this. Okay, so this is a function R. Okay, as a function of this. So if I want to maximize this, because it's decaying nature, so I have choose minimum value of this exponential. This, so I have to minimize this. Yeah, minimize this. So with the help of 1314 for ML detection, maximizing this equal to the minimizing this, that can be also minimize this, and this can be defined as a distance matrix like this. Okay, so in maximum likelihood, we are in place of maximizing, we are minimizing the this can be treated as distance between Euclidean distance between received vector and transmitted signal vector Sn. Suppose this is transmitted signal vector. So due to noise, I will get this point. So this is noise, this is this. So this is received vector. If you are subtracting vector r minus Sm, this is distance between. Okay, so we want to minimize this distance. So for AWG, ML criteria is equivalent to the minimum distance detection. So ML detection is also known as a minimum distance detection. We will simplify this distance matrix, that is called distance matrix. Sometimes people ask define a distance matrix for the ML detection. So that is this. So this will be equal to this. Square this term, rk square minus 2rk into smk plus smk square. Take summation inside, and I can write three summations like this, this again. This summation is again can be square of norm of received vector, and this can be written as inner product of received vector with Sm, and this is square of this square of norm of SM, transmitted signal vector. Okay, so we can observe that we have to vary M because received signal is fixed. So now I have to calculate, there are so many constellation points in this space. Okay, I have to calculate this distance d1, d2 like this. This distance matrix corresponding d of r corresponding, this is s1, this is s2, this is s2, this is distance matrix r s1 and so on for m points. So we know that this is a common to all decision matrix, hence it may be ignored in the computation of the matrix of this matrix computation. So the modified distance matrix that is denoted by d prime of r comma sm, because we are ignoring, this is a constant for all calculation. Okay, so this can be written like this. We know that this is inner product between r received vector r and constellation point Sm, the transmitted signal point Sm. This is projection of received vector on each m possible transmitted signal vector Sm. In other words, this is a measure of correlation between R and vector R and Sm. This is correlation. Correlation can be similar in similarity measure discussion. We have discussed that correlation is related with. We can define this correlation in terms of inner product of the signal also. Okay. So now we can define a new decision matrix that is called a correlation matrix like this. This is minus of modified decision distance matrix that can be written like this. Okay, so now we can write three equivalent rule for the ML detection, a criterion. Maximize this likelihood function that is equivalent to the minimizing the distance, and then another way we can say that you have to maximize the correlation between R and Sm. Okay, hence for ML detection rule I will define this is decision rule. You have to maximize the correlation between R and all possible Sm. So thus correlation matrix will compute for deciding which was M signal was transmitted. Similarly, for MAP criterion, a posteriori probability matrix defined like this, because this posteriori a posteriori probability can be written as conditional probabilities like this. This term is a constant. So calculating this, I can only calculate this because this is constant for all Sm for given R. So we'll define a posteriori probability matrix like this. This is multiplication of prior probability of Sm into conditional probability of R given conditional probability of R given Sm. Okay. Hence, for MAP detection rule is this, maximizing this posteriori probability matrix. So let us summarize about this detectors. So from previous discussion, we can say that the function of this detector is compute a set of M matrices and select the signal corresponding to the largest matrix. For MAP based detector, compute this posteriori probabilities, a posteriori probability matrix, and decision S cap. Suppose you have calculated M and you find that a posteriori probability matrix corresponding to S2 is a maximum, then S hat will be the S2. Similarly, for ML based detector, compute this correlation matrix between R and SM. So there are M points. Suppose we find that in capital M correlation matrices, we find that this correlation matrix corresponding to S5 is maximum, then S hat will be the S5. Decision is S5. So you understand how detector works. Okay, let us take one example, numerical example, and discuss. Consider a case of binary PAM. Binary PAM means capital M equal to 2, in which two possible signal points. So SM, this set consists of only 2 point S1 and S2. Okay, here S1 is equal to square root EB, minus S2 equal to square root, which means that S2 will be the minus EB, and the prior probability of PS1, P of S1 is P and P of S2 is 1 minus P. Total probability should be 1 because probability of PS1, probability of PS2 should be 1. Determine the matrix for optimum detector when transmitted signal is corrupted with additive white Gaussian noise, that mean is 0 and variance and not by 2. So given is prior probability like this, let us draw the constellation diagram. So this is constellation diagram. This is S2 is minus EB and S1 is square root EB. Okay. So received vector, because it is binary PAM is one dimensional signal. So for binary PAM, received signal R can be written as, that is SM plus N, where N is a zero mean Gaussian random variable with variance sigma square, that is equal to N naught by 2. When N equal to 1, S1 will be square root EB. We can write R equal to square root EB plus N. When M is equal to 2, S2 will be minus square root EB. We can write received signal RK is minus square root EB plus N. Because N is a, since random variable N is a Gaussian random variable, zero mean and variance this, then for given S1, conditional random variable R given S1 is also, we can calculate, it is a Gaussian random variable with mean square root EB and variance this. Similarly for this, mean is minus EB and variance is N naught by 2. So we can write the conditional PDF for these two signal like this and this, because then I will calculate the matrix, posterior probability matrix corresponding S1 and S2. This is posterior probability matrix corresponding to S1, that is equal to multiplying the prior probability of S1 into conditional probability of R given S1. Okay, so this is this, and probability of PS1 is P, so multiply, I will get this one. Similarly, I will calculate the a posteriori probability matrix for S2 like this, I will get this. So decision rule may be expressed like, when this a posteriori probability corresponding to this signal S1 is greater than a posteriori probability matrix corresponding to S2, then decision will be S hat will be the S1. On the other hand, if this posteriorly a posterior probability matrix corresponding to S1 is less than a posterior probability matrix of corresponding S2, then S hat will be the S2. This comma S1 S2. Divide both sides by this term, so I can write this is ratio of both, this is greater than 1. So I can express like this. If this is greater than 1, S hat will be equal to S1. Again, 20 can be re-expressed like this. Divide by this. So less than 1, decision will be S hat will be S2. Both can be expressed like this type. Means this ratio is greater than 1, so decision will be S1. If this ratio is less than 1, decision will be S2. Okay? Sometimes as had people don't write for easy for representation. This is a standard way to writing this optimum MAP decision. So now we calculate this ratio. This is ratio. Okay. So after substituting and simplifying, I will able to get this. Now I will substitute this ratio in this case. I will get this one and rearrange. I will get this one. Take natural logarithm both sides and simplify. I will get this is this, and this term right side, this term is known as a optimum threshold for detection. Threshold for detection in case of binary pair. Suppose consider two cases: equiprobable case and non-equiprobable case. Equiprobable means small p should be half. It indicates that prior probability are of S corresponding to the S1 and S2 will be half. That is case equiprobable. If p is half, so 1 minus half will be 1. This 1 minus half is half divided by half, that is 1. So log 1 is 0. So this is optimum threshold. Sometimes people are asking what is the optimum threshold for equiprobable case. So this is optimum threshold. Optimum threshold is 0, and knowledge of the value of noise per spectral density parameter N naught is not required by detector in order to compute this threshold. If in equiprobable case, this threshold is 0 and it doesn't require knowledge of this noise per spectral density parameter. Okay. Another case, when p is not equal to 1, then unequal prior probabilities. In this case, this will be the optimum threshold. And what is the problem with this optimum threshold? It indicates it necessary to know the not only value of prior probabilities but also the value of noise per spectral density parameter N naught in order to compute the thresholds. Okay. This is about the design of optimum detector, and there are two types of optimum detector based upon decision criteria, MAP criteria and ML criteria. Okay, thank you for watching the lectures. I am taking material from this books. You can refer for more, and you can refer this books for more understanding. Thank you for watching the lectures.